Anyone who has waited at a rail crossing after dark knows exactly what it looks like. A triangle of white light, a single powerful lamp riding high, a pair of smaller ones mounted down low, all three burning through the night straight at you. The arrangement feels timeless, as if locomotives were always built that way. They weren't. For more than 160 years, a locomotive carried exactly one headlight and nothing more. So what took until 1996 for anybody to bolt on the other two? The answer winds through burning firewood, a Chicago firefighter, a Canadian mountain pass, and one of the strangest 20-year delays in transportation history. The story opens in 1831, when the South Carolina Canal and Railroad Company became the first American line to attempt running after sunset. Its answer to the darkness was almost comically primitive. A flat car shoved out ahead of the engine, carrying an open fire of burning pine knots. That wavering orange light revealed perhaps 40 or 50 feet of rail, sufficient to catch sight of a stray cow or a downed tree, and nothing beyond. The man at the throttle behind those flames was, for all practical purposes, operating on blind trust rather than sight lines. Enclosed lanterns fitted with reflectors displaced the open flames within 10 years or so. The Boston and Worcester Railroad fielded one of the earliest around 1840, quite possibly nothing more than candles set behind glass. Oil lamps took over as the norm through the 1850s, and once Irving Williams brought kerosene to locomotive headlamps in 1865, night operations finally had a dependable fuel. Those kerosene units ballooned to remarkable dimensions, certain examples reaching 26 inches in height and 23 across, their brass bodies adorned with hand-painted scenery and portraiture. Gorgeous artifacts, every one of them prized by collectors today, and by any modern measure, astonishingly feeble as actual illumination. Electricity delivered the true breakthrough. The Westinghouse Air Company, beginning in 1881, ran experiments substituting electric lamps for oil. The carbon arc threw a beam so ferocious it would momentarily blind crews on trains coming the other way, a side effect that took decades to properly tame. Edison's patented incandescent bulbs, meanwhile, couldn't survive the constant shaking of a working engine. The breakthrough arrived in 1897, when Robert Pierce perfected the first production-ready electric locomotive headlight, marketed through a firm he founded, the National Electric Headlight Company. Inside 8 years, 20 American railroads had put his design to work. By mid-20th century, the industry had settled on the sealed beam unit as its standard, a tungsten filament seated in a parabolic reflector, sealed away from weather and vibration, throwing a concentrated beam capable of revealing a person 800 feet down the line. Federal regulators eventually wrote that performance into law, with the Federal Railroad Administration demanding a minimum peak output of 200,000 candela from every road locomotive. To put that in perspective, it's on the order of 400 times the intensity of an automobile's high beams. 200,000 candela, 800 feet of forward reach. Surely that's ample light to protect everybody. Except consider everything that one brilliant lamp fundamentally cannot communicate. It cannot inform a driver idling at a crossing how quickly the machine behind it is closing, or how far off it sits, or how many seconds remain before 12 million pounds of steel and cargo arrives at the pavement. Here, the limits of human vision slam into the momentum of a freight train. Human eyes judge range and velocity impressively well, but only when given landmarks to compare. An automobile presents two headlamps roughly 4 feet apart, handing your brain a matched pair of markers. As it draws near, the gap between them visibly spreads, and your mind computes closing speed from that spreading without you ever noticing the calculation happening at all. A lone point of light supplies zero such data. Is it a mile out doing 70 miles per hour, parked half a mile up the track? From the crossing, there's no telling. At long range, its brightness shifts so slowly that no eye alive can separate a moving train from a parked one until the engine is frighteningly near. Weigh the stakes. A loaded freight outmasses a passenger car by a factor of around 4,000, roughly the relationship between your car and an empty soda can under its tire. 100 loaded cars, rolling at 50 miles per hour, demand something close to a full mile of braking to reach a standstill. Swerving isn't an option that exists. Stopping gets measured in thousands of feet. Once a driver miscalculates that solitary oncoming light and rolls onto the rails, the people in the cab are reduced to spectators, hands on a brake that cannot possibly act in time. The industry grasped all of this for generations, and its engineers and safety departments picked the problem apart from every direction. Yet, the first genuine fix came from a man with no railroad background whatsoever. In 1936, Jerry Kennelly, a firefighter in Chicago, hit on the insight that a light in motion, sweeping or looping through a figure eight, would seize a motorist's attention far faster than any fixed beam. He brought the idea to the Chicago and Northwestern Railway, which agreed to trial it aboard the 400, its premier passenger run. Out of that test came the Mars Light, a mechanically driven headlamp whose cranks and linkages swung the beam up and down, side to side, or both together, painting its signature figure eight across the darkness ahead of the engine. And it delivered, immediately and measurably. Drivers registered a swinging beam dramatically earlier than a fixed one, and the improvement was obvious enough that competing lines paid attention. Across the late 30s and through the 40s, Mars Lights spread onto passenger power nationwide. Kennelly incorporated the Mars Signal Light Company, engineering variants for every duty, from streamliners to freight assignments. The Nickel Plate Road signed on, as did the Rock Island, the Milwaukee Road, and the Burlington, every one of them a repeat buyer. The Mars approach didn't hold the field alone for long, though. Pyle National entered with the Gyrolite, sweeping its beam in circles or ellipses rather than the figure eight, giving railroads a choice of patterns. By the 50s, a swinging headlight had become an everyday sight across the business, above all on passenger runs threading busy station districts. Preferences varied from company to company. Santa Fe fitted them to passenger diesels while leaving its freight power bare, whereas Southern Pacific went the opposite direction and outfitted virtually its entire road fleet, engine after engine. But none of this touched the underlying problem, and the hardware carried weaknesses of its own that time would expose. Mars Lights and Gyrolites alike were mechanical contraptions, stuffed with gears, cranks, and motors demanding constant attention. The dual crank movement inside a Mars unit looked graceful in operation and behaved like a diva in the shop, and holding hundreds of them in calibration across an entire roster turned into real money. When the lean, cost-slashing decades of the 60s and 70s arrived, that expense stopped surviving budget reviews. Southern Pacific, the deepest believer of them all, stripped every oscillating unit from its fleet almost overnight. Come the early 80s, factory-fresh locomotives carrying any auxiliary lighting at all had become rare, and the swinging beam slid into obsolescence. After 50 years of experimenting with moving light, the American locomotive stood right back where it started. One lamp, alone, on the nose, exactly as it had been in the kerosene days. And people were still dying at crossings, year after year, in numbers that never meaningfully budged. While the American industry was tearing its oscillating lights off in the 60s, a very different experiment was unfolding in the Canadian West. Canadian National Railway worked a line linking Jasper, Alberta with Prince Rupert, British Columbia, a corridor blasted through some of the harshest country in North America and infamous for rockfall and slides that could bury the rails without warning. A crew hammering through those mountains after dark, guided by nothing but one beam pointed dead ahead, stood every chance of meeting a boulder sitting square on the right-of-way with no time left to act. Canadian National's remedy was modest and eminently sensible. 2 extra lamps bolted low on the locomotive's nose, angled outward, washing light across the shoulders flanking the track. Nothing oscillated. These were plain fixed beams, installed so crews could see what waited just off the rails in the drainage cuts where slide debris liked to collect. The men who ran them, with the plain-spoken efficiency of working railroaders, gave them the obvious name: ditch lights. Then something nobody planned happened. The lights earned their keep almost immediately, and not merely against rock slides. Working together with the headlight overhead, the two low fixtures formed a luminous triangle detectable from far beyond the range of any single lamp. Better still, that triangle handed observers 3 fixed markers where one had been, and suddenly drivers waiting at crossings could genuinely read how fast the machine was coming and how far away it sat. In 1974, a Canadian Pacific movement plowed into slide debris its crew never saw coming. The wreck triggered a federal inquiry, and the investigators' report stated that the derailment probably wouldn't have happened had the engine-worn ditch lights of the type Canadian National had been operating for years. 12 months on, in 1975, Canada made ditch lights compulsory on every locomotive in the nation. The United States would need over 2 decades to arrive at the same conclusion, and explaining those lost 20 years, with the evidence sitting in plain view the entire time, is the most uncomfortable part of this whole story. Through the 1980s and deep into the early 1990s, U.S. railroads kept dispatching engines wearing a single lamp. The Canadian evidence was in. Canadian fleets had run the equipment for over 10 years, with results you could measure. South of the line, nothing moved, and the explanation was far less about safety than about money and bureaucratic gravity. Fitting new lights to thousands of units costs serious capital, and absent a federal requirement, no railroad owed anyone the expense. Culture did the rest. Railroading is an inherently conservative trade, resistant to any change that neither regulation nor economics forces upon it. All the while, the carnage at crossings ground on, with something like 2,000 Americans killed or hurt at highway-rail intersections annually, and 94% of those wrecks traced to the drivers themselves, people who misread the oncoming train's speed and range, or never registered it at all. Quick pause. If this kind of story is your thing, take 1 second and subscribe. New railroad history and engineering lands here every week. So, what finally broke the logjam? The Federal Railroad Administration was fully aware of Canada's results. Early in the 90s, the agency commissioned a run of field trials to nail down the most effective method of making locomotives conspicuous at crossings, and they threw everything at the wall. Mars-type lights, gyrolights, ditch lights, strobes, rotating beacons, each configuration evaluated under real conditions at test sites scattered around the country. The findings came back unambiguous. Every auxiliary arrangement beat the solitary headlight, stretching the distance at which observers first picked up the train and sharpening their estimates of when it would arrive. Within the field, fixed beams aimed dead ahead in a triangle with the headlight, so-called crossing lights, scored highest for raw detection range, while ditch lights angled slightly outboard did the best job of showing crews the right of way. The agency's answer: permit both layouts, plus strobes, under the rule it was drafting. The Federal Railroad Administration issued its final regulation on auxiliary locomotive lighting on March 6, 1996, filed as Section 229.125 under Title 49 of the Federal Code. Every active locomotive across North America would wear a different face because of it. The core mandate read plainly: any lead unit running faster than 20 miles per hour over public crossings at grade must carry functioning auxiliary lights alongside its headlight. The fine print was exacting. 2 white auxiliary lamps mounted on the front, positioned so that, together with the headlight, the 3 lamps drew a triangle. Minimum height, 36 inches above the railhead. Where the vertical gap between headlight and auxiliaries reached 60 inches or more, the pair needed at least 36 inches of lateral separation. Where that gap fell under 60 inches, the required spacing widened to 60. Each lamp had to deliver no less than 200,000 candela. The compliance deadline for the entire national fleet, December 31st, 1997. And running a unit past 20 miles per hour through a crossing with dead auxiliary lights wasn't a slap on the wrist. It constituted a violation of federal code. One carve-out survived, and it says everything about how railroads treasure their heritage. Any locomotive constructed before the last day of 1948, provided it was not hauling regular commuter or intercity passengers, qualified as historic equipment and escaped the mandate. That clause is the reason Southern Pacific 4449, the celebrated GS-4 steam engine that hauled the Olympic Flame in 1984, still runs behind its original Mars light with no ditch lights in sight, and why heritage diesels on tourist lines and short lines may lawfully go without, so long as they hold to 20 miles per hour or less through crossings. For everything else on the roster, tens of thousands of working units, the countdown had started. What followed ranks among the swiftest fleet-wide hardware conversions the modern industry has ever pulled off. From 1998 onward, every unit leaving the erecting halls at General Electric and Locomotive carried ditch lights from the factory. Out on the network, shop forces attacked the older power, drilling mounts and pulling wire to hang fresh housings on hundreds of engines everywhere from Jacksonville to Omaha. For a brief transitional window in the late 1990s, a crossing was a time machine. An unmodified unit would rumble past with its lonely single lamp, chased minutes later by a freshly converted engine showing off its brand new triangle, two eras of railroad practice sharing the same stretch of track. How each company applied the rule ended up revealing its personality. In the East, Norfolk Southern and CSX specified flashing ditch lights, betting that an alternating pulse would cut through a distracted driver's fog more effectively. Out west, BNSF and Union Pacific, joined by the Canadian roads, stuck with steady beams. Norfolk Southern and Canadian National both exceeded the letter of the law, ordering new power with ditch lights at both ends because their operations routinely ran engines in either direction without turning. Amtrak standardized flashing units across its locomotives and cab cars, while also keeping crossing lights, those fixed straight-ahead beams, as one more layer of conspicuity. Metra, Chicago's commuter operation, held on to its gyro lights even after fitting ditch lights, stacking half a century of lighting doctrine onto single machines, old technology, and new burning side by side. CSX even worked out a field fix for the day. A lead unit dies, and the trailing engine must run long hood forward, with no ditch lights on its rear end. Crews carry magnetic ditch lights that clamp on and draw from the locomotive's power supply, temporary hardware that keeps the train at track speed and inside federal code rather than parked. Small detail, big message about how seriously the rule is treated, because an engine with dead ditch lights doesn't get a friendly reminder. It gets throttled to 20 miles per hour through every single crossing on its route, a crawl capable of adding hours to a schedule and rippling delays across a whole division. What separates one lamp from three isn't luminosity, it's geometry. One point of light, on its own, gives your visual system nothing to anchor on, so its motion stays undecipherable. 3 points locked in a familiar arrangement supply enough structure to triangulate range and read closing velocity. As the engine bears down, the triangle visibly widens, firing exactly the depth perception response a lone beam can never trigger. The principle is identical to why paired car headlamps work. Two separated sources create an angular spread that grows with proximity. The locomotive's triangle simply advances the idea by adding height, a vertical axis that renders the oncoming shape impossible to mistake for anything else. Nothing on any road or railway resembles a white triangle of light, point down, closing on your position, and that uniqueness is itself protective. A driver doesn't have to reason about what's producing the glow. The shape alone announces one word: train. Inside those three fixtures, the technology has never stopped moving. Through most of the 20th century, the lamps were sealed beam incandescents in the familiar PR56 format that had ruled since dieselization. Halogen bulbs later displaced them, burning brighter and lasting longer. The genuine revolution began in the decade after 2010, once LED units finally reached the brightness and toughness locomotive duty demands. An LED headlight runs beyond 50,000 hours against roughly 2,000 hours for halogen, and sips as little as 20 watts where halogen swallows 200 watts, trimming the parasitic drain on the engine's electrical system. And that detail carries more weight than it sounds. Any watt feeding a lamp is a watt withheld from traction and multiplied across thousands of units. The fuel numbers become real. Current LED assemblies also carry integrated heating elements, marketed as smart heat, to keep lenses clear of snow and ice through winter. Halogen never needed the feature because its waste heat did the job by accident. LED units run cool enough that, without a heater, the first serious storm of the season would frost the lamp blind. It's the classic engineering pattern where solving one problem births the next. The Federal Railroad Administration published guidance in 2020 smoothing LED adoption, and by the middle of this decade, nearly all new power ships with LED headlights and matching LED ditch lights installed, while the venerable PR-56 sealed beam, half a century of faithful service behind it, fades from every Class 1 roster. Yet all the progress hasn't erased the original problem. Federal figures for 2025 logged over 2,200 collisions at American grade crossings, killing 286 people and injuring more than 700. Grim as that reads, it's a world away from the darkest stretch of the 70s and 80s, when crossing deaths regularly topped 1,000 a year. The three-light triangle, together with better gates, clearer signage, and public awareness campaigns, has spared thousands of lives across 30 years. Still, nearly 300 people died at crossings last year, and 94% of those collisions came down to driver behavior. People who never looked, never stopped, or misjudged 12 million pounds of moving steel in the dark. The lights are burning. The triangle can't be missed. The perceptual science all checks out, but geometry only saves the driver who bothers to look up from the wheel. So the next time you're stopped at the gates watching those three white points spread wider in the blackness, consider everything packed into them. 150 years of iteration, running from burning pine knots through carbon arcs and sealed beams all the way to the LED era. A Chicago firefighter who grasped that motion is what hooks the human eye. A Canadian railroad that aimed lamps at its ditches and stumbled into solving a problem that had claimed thousands, and a federal rule that trailed Canada's lead by 2 full decades. 3 lights, 1 triangle, riding the nose of every working locomotive on the continent. Not because anyone liked the styling, because 1 light, however powerful, was never going to be enough.